Hello and welcome to this video about proofs of theorems in linear algebra. In this video, we'll study a proof involving the rank and nullity of a linear transformation. But first I want to prove another theorem that will be used by this theorem. I decided to break this theorem up into two theorems, which is different to the textbook. I did this so as to make this proof easier to follow, and I've boxed the formulas that we ultimately want to prove. And here are some definitions that I want to make. The nullity is the dimension of the kernel, and the rank is the dimension of the image. We'll explore what rank is in some future proofs. So now we'll start by explaining the statement of the first theorem. We'll firstly have a set of vectors, and they are all non-zero, and this set is linearly independent, or Li. And none of these vectors are in the kernel of this linear transformation. And so this set of vectors that are the output of the linear transformation L will be non-zero and linearly independent. So now to prove this, we'll write out this set of vectors again. So if we apply this equation to this set of vectors, then the only solution to it for these constants is 0, because that's the definition of linear independence. So we can apply the linear transformation to this equation, to both the left and right hand sides. And from a previous theorem, this equation will be equal to the 0 vector. We can use a previous theorem to break this function up into a sum of these functions. And these vectors will be linearly independent too, because the constant c1 to cn being equal to 0 will be the only solution for this equation being equal to the 0 vector. And this proof can go in reverse, so if the outputs of this function are linearly independent, then their inputs will be too. And now to prove the main part of this theorem, which is part B. We'll define all of these functions and vector spaces here. It's important to note that these vector spaces are finite dimensional. And this theorem says that this equation is true. It can be thought of as the number of basis vectors for each of these vector spaces. So now to prove this theorem, we'll let the dimension of the vector space V, which is the domain of the function, be set to be equal to n. We'll set the dimension of the kernel to be equal to k, and we'll assume that k is any number between, but not equal to, 0 and n, although this proof should work for these numbers too, but this is the way it's set out in the textbook. So we'll set the basis for the kernel of L to be equal to this set of vectors, and there are k of these vectors, which is the dimension of the kernel. And these are another set of linearly independent vectors in V. And these vectors, together with the vectors in the kernel, form a basis for all of the domain, which includes all of the vectors in the kernel, and all of the vectors which will form the image, which can be thought of as the pre-image. So all of these vectors will span the image of L. And because some of these input vectors are in the kernel, then that will cause these vectors to all be 0, because that's the definition of the kernel. It's helpful to write down every step, because they aren't obvious when you have to write down 10 or more steps. So I'll just scroll the screen up a bit to make more room for the proof. Because these vectors are all 0, then we only need these vectors to span the image of L. And we can write this out in math notation using the spanning function S. So now we have to show that this set is linearly independent, so that it can be shown to be a basis for the image of L. We'll invoke this theorem to do this, that we've already proven earlier in this video. So we've got these two conditions, that this set is linearly independent and that these vectors aren't in the kernel. So we can use these two results and this theorem to prove that this set of vectors in the image of L are linearly independent. I thought it would be easier to prove this result first and make it into a separate theorem, and then invoke it in this theorem. And so we can say that this set is a basis of the image of L because it both spans this set and is linearly independent. And then we can use this set of basis vectors to calculate the dimension of this vector space, which is n minus k. I'll just scroll this page up, and I'll write this reason down. The dimension of the image of L is equal to this number, because that's how many vectors there are in its basis, and the number of basis vectors will always be the same for any basis. So now we'll evaluate this formula by substituting the values into it. After substituting the values in and evaluating the equation, we get the value of n. And n is equal to the dimension of the domain V. So we've done it. We've proven this equation true, which is the aim of this proof. I think it would work if k was equal to n or 0, but I'll put these in separately because some mathematicians won't be satisfied. So I decided to do these n cases where one of these sets only contains the 0 vector. We'll start with the case where the dimension of the kernel is 0. So the kernel contains only the 0 vector and therefore contains no non-zero vectors. So we'll let this set of vectors be a basis for the domain V. Then these vectors will span the image of L because there are no non-zero vectors in the kernel. Every vector in V will map to a non-zero vector. So by the theorem we proved in the beginning of this video, this set is linearly independent. A set of linearly independent vectors in the domain will map to a set of linearly independent vectors in the image, if none of them are in the kernel. And so this set satisfies all the conditions so as to be a basis for the image of L. We can write out here in math notation that this set spans the image of L. And because there are n vectors in this basis set, then the dimension is equal to the number of vectors that it contains. So now to invoke the equation that we're trying to prove. We'll substitute in and evaluate the values for these quantities that we found in this proof. And so we've proven this formula to be true for the case when k is equal to 0. Now to prove it for the case where k is equal to n, that is, where everything is in the kernel. And the image of L will only contain the 0 vector because everything's mapped to 0, and therefore there are no non-zero vectors in the image of L. And so the dimension of the image of L is 0. And so now we can invoke this equation that we're trying to prove. And after substituting the values in and evaluating them, we find that this proof is true for the case where k is equal to n. So we've proven this for all possible values of k, and so we've finished the proof of this theorem. So I hope that you found this video to be helpful and interesting. Please click like and subscribe if you did. Feel free to share this video and to write helpful thoughts and ideas in the comments. And thanks a lot for watching.